My name is Gabriel Geffen, and I'm a third-year PhD student at the University of Arizona, working under Dr. Yao-Zhan Wu. My research focuses on transportation resilience, and one of my biggest goals is to harness existing infrastructure while integrating emerging AI and machine learning techniques to build practical tools that make our transportation systems safer, smarter, and more sustainable. That's where TISMO comes in. To me, TISMO represents real-time problem solving and finding ways to make better use of what we already have. I'm here today at the Center for Applied Transportation Sciences, where I've been working since my junior year of undergrad. Behind me is our TV wall, which connects to live roadway cameras across Arizona. We use it for both operations and research, and today as a great screen for walking you through this project. My passion for transportation engineering goes as far back as my sophomore year of undergrad. I worked in a mechanical and aerospace engineering lab where our research often fell far from public impact, which is a very disheartening truth. While that experience helped me develop strong technical and programming skills, I wanted to see real-world outcomes. TISMO has been that bridge for me, using data, technology, and collaboration to deliver immediate benefits in mobility, safety, and sustainability. That's what excites me most. The project I'll highlight today is part of NCHRP 0734, AI for TISMO applications. This effort recognizes that while we have powerful tools like ramp metering and variable speed limits, deciding when and how to deploy them is very complex. Traditionally, these decisions rely on predefined rules that don't always adapt to changing conditions. AI-enabled decision support systems, or DSS, can overcome that limitation by learning from data and providing smarter, real-time recommendations. In this video, I'll discuss one case study within that project, ramp metering on Arizona's Loop 101 corridor. This case study focused on improving the reliability of detector data. Reliability is essential because inaccurate sensor readings can lead to incorrect metering decisions and reduced corridor performance. The analysis covered 3 weeks of evening peak data and used correlation-based methods to determine where detectors drifted or consistently underreported speeds. The main goal being to develop correction models using relationships between reliable detectors and crowdsourced data such as INRIX. The key takeaway from the results is that some detectors showed systematic biases during peak periods, which can impact the accuracy of ramp metering. These plots clearly highlight how some detectors show major differences in true or expected speeds. By applying the values generated from these correction models, we can recover realistic speed trajectories even when sensors failed or provided unreliable data. But why does this matter? Because these correction models can feed directly into ramp metering algorithms. Higher quality data means better metering decisions, smoother merging, more stable mainline flow, and ultimately, fewer delays. This case study shows how AI-style logic, from recognizing patterns, comparing sources, to automatically correcting data, can be embedded in TISMO operations. Beyond this specific corridor, agencies could automatically monitor thousands of detectors statewide to identify issues early and combine traditional sensors with crowdsourced data for more resilient operations. And by sharing these lessons nationally, we're helping DOTs everywhere move toward data-driven, adaptive traffic management that benefits the traveling public directly. For everyday drivers, this translates into quicker, more advanced applications of TISMO that will surely lead to reduced stop-and-go traffic, less crash risk, and even fuel consumption. At the system level, this approach gives agencies the ability to automate sensor quality control, and that means better targeting of maintenance resources, better integration of crowdsourced data, and more resilient control strategies during incidents or peak demand. And within the broader NCHRP 07-34 framework, our case study contributes to a national guide that will help agencies confidently deploy AI for DSS. Working on this project has shown me how a seemingly small problem, like a few faulty loop detectors, fits into the bigger vision of AI-driven transportation management. It's inspiring to see how careful data analysis can ripple outward into policy, investment, and real-time system improvements. This experience has strengthened my passion for advancing AI for public sector decision-making, and it's pushed me to continue bridging the gap between academic research and real-world TISML operations.